off too when I'll start the recording again. So I guess Rachada will stitch these things. Sorry. It's not my fault, you can blame Apple for it. Okay, so I'll have to do this since something doesn't get powered on. Okay. Basically, somehow you take these biased branches and predict them with a simple predictor. Now you can imagine maybe the compiler marks these branches and they don't even get predicted through the hardware mechanisms, right? And you can read this paper if you're interested in that. Okay. Let me cover some other branch predictor types and we'll take a short break. I guess I'm going slowly, so we'll breeze through the rest of the lecture. But hopefully everybody understood these concepts because these are very fundamental concepts. Actually, this is a very interesting field, and this is a very hard problem to solve. People have developed many other things, loop branch detector and predictor. This works well for loops with small number of iterations where the iteration count is predictable. You can just filter that out. You can figure out what's a loop. And this is where the compiler could help. Although existing processors have loop predictors that detect the loops and predict them. I'm not going to go into how that is designed. People have proposed things using machine learning for branch prediction. Basically, one idea is the Perceptron branch predictor. What we've seen over here in the global, let's look at the global predictor. You have a global history register, right? What it's really trying to do is to correlate the outcomes of the last n branches with the outcome of the current branch. But maybe you don't really care about the last n branches. Let's say your history register is 12 deep, or its length is 12. You look at the last 12 branches just like an alpha. Maybe there's only one branch that determines the direction of this branch. Because not all branches are correlated. I've shown you some examples. Some branches are more strongly correlated, but there may be another branch testing some other random condition that has no relation to this branch's condition. So the idea of Perceptron branch predictor is to learn the direction correlation between individual branches and assign weights to those correlations. Basically, the 8th previous branch is much more correlated with this branch than the 2nd previous branch. So use the direction this 8th previous branch went as an indicator of the direction of the current branch that you're predicting. Why? Because they may be testing the same condition almost, right? They depend on each other based on my examples. Whereas the other branches in the history may have nothing to do with the prediction for this current branch. So this is more sophisticated. It's more complicated because now you have weights instead of taken, not taken values. Does that make sense? And you can have positive or negative correlation. If this branch is taken, this could be not taken. And you capture this based on the value of the weights. If a weight is negative, that means you're negatively correlated. If the weight is positive, that means you're positively correlated. And Perceptron is one way of implementing this idea. Perceptron is basically a very small neural network that can capture correlations between different outcomes. And that's what we do. It's kind of beautiful, right? It works better. This works a global version of this works much better than the global predictor that we've discussed. It has about 20% less misprediction rate. And now you know the importance of 20% less misprediction rate, right? And this is a paper if you're interested in this. This was published in HPC, High Performance Computer Architecture, in 2001. So it's relatively recent. Other ideas, I'll just throw you some ideas I'm not going to test you on some of these, although you may want to think about this just to exercise your creative juices. Geometric history length. So people have found out again that one history length may not be good. For some branches, you want to look back 1,000 branches back because there's some branch that tests the same condition 1,000 branches ago. For some branches, you don't care. You just look at the previous branch. So how do you design a predictor that caters for both? Obviously, if you design a predictor that has a history length of 1,000, your table is insurmountable, right? How do you design a table that has 2 to the 1,000 entries? Well, you could. Anything is implementable, but at what cost, right? So you don't want to do that. So people have looked at geometric history length predictor, well, I guess your predictor is not geometric history length, but the idea over here is to have a set of tables with different history lengths where the history lengths actually grow as a geometric series. And now you get much better accuracy in your prediction because different branches are predicted by different tables in this case. It's kind of a cute idea actually to do this. But then how you design this becomes important. Which tables do you update? Which one do you not update? Because you definitely don't want to update the 1,000 history length table with every branch. Right? Somehow you need to figure out which branch should be updated, which one. I'm not going to go into that, but people have actually put a lot of thought into designing this because this has been a very hard problem. And maybe you'll put some thought also. Actually, maybe we'll give you enough flexibility to put this thought in one of the later labs. Okay, let's take a short break right now and come back at 1:50, and then we'll cover predication, and hopefully we'll be done with it. Is it recording? Hopefully. Okay, so hopefully that gives you an idea of this solution. Yes, the next fetch address. I guess I don't have any more, so I'll do this, which is branch prediction. This has been a fascinating topic, but hopefully you have some insight into why these things work. If I had given you just the implementation without the underlying reasons why this would work, would it be interesting to you guys? Or now do you have a good idea of why it makes sense to build histories this way? Okay, hopefully. Still sometimes, it's still fascinating that you can predict 99% accurately the branches, many branches. It's just amazing. Okay, let's take a look, but even that is not enough. So people have looked at other solutions. So we're going to look at one solution, which I think is promising, especially when you combine it with branch prediction. And we'll take a look at how to combine it with branch prediction. This is eliminating control flow instructions, and this is one way of eliminating control flow instructions that we've looked at, predicate combining, and compilers do that today, and maybe you do that in your code today, so I'm not going to cover this again. But predication we've also covered, so I want to go into a little bit more depth into this. The idea was to have the compiler convert the control dependence into data dependence. This way, branch is eliminated. And how does this work? Basically very similar to what you're implementing with ARM. Each instruction is a predicate bit that is set based on the predicate computation. And only instructions with predicate values that evaluate it to true are committed. Committed meaning they affect the architectural state. Everything else turns into null. If the predicate value is false, it's a null. Let's take a look at this very simple piece of code, if then else. If condition is true, then B set to 0, else B set to 1. And this is the control flow graph for normal branch code with branches. Basically, you set the predicate into a register. Let's assume that it's a general purpose register based on the condition, and then you check the condition. If the condition is true, you jump to the target, otherwise you go to the default through path, right? And the fall through path moves 1 into B, and then avoids the target, so you have an unconditional jump to avoid this target. And then the target moves 0 into B and then goes into the merge point. This is called a merge point. So this is also called the Hammock Branch also. It's like a hammock. You have two paths. Predicated code looks much nicer in terms of the control flow graph. It's straight line code, right? Basically, condition computation is the same. Result is stored in a predicate register. And you basically combine both paths, the taken path and the not taken path, or true path and the false path. And if the predicate evaluated to false, then 1 is moved to B. If the predicate evaluated to true, then 0 is moved to B. Basically, you have two predicate registers, or predicate register and its complement. Very similar to ARM. Different architectures implemented differently, but that's how it is. And this is something to keep in mind. Let's assume that you have some code over here, which I should have added over here too. But let's say you're adding 1 to B later on and storing the result in X. In this code and this code, you still have the same instruction, but during execution, think about what happens to this. If you have branch code, you're predicting the branch, And you can execute this right away, right? Because you're going through one path, and the data value is one thing. But think about what happens over here. Basically, B, you're waiting for the value of B, but B can come from this instruction or this instruction. And until the branches resolve, you do not know which version of B you will take. What you've done is you've converted the control flow dependence into data dependence, and everything that's dependent on that path is now cannot be executed until the branch is evaluated. Does that make sense? Yes?
But aren't you still just wasting cycles executing no ops?
Yes, so that's the downside. So now you're looking at the downside. So one downside of this is basically you're executing no ops. But the other downside is you cannot execute this instruction. Whereas if you're predicting, you can execute this instruction. Right? You have to wait until the predicate value is resolved. Okay. So you've added one more disadvantage. We'll get to the disadvantages. I guess we can cover it right now. One disadvantage of predicate execution. Let's talk about the advantage first. Always be optimistic. Talk about the good thing first, right? What is the good thing? Now the branch is gone. You don't need to predict it, right? Beautiful. And you can remember we talked about compiler optimizations. Now the branch is not hindering those optimizations. You can move code freely over here, assuming it's safe and correct, as we've discussed. Those are two advantages. The disadvantage is, well, you're always wasting work. Whenever you eliminate branches, you waste work, right? You do useless work. Because either this one or this one is really going to take effect. The other one is going to be an off. And this wasted work may be huge, depending on the size of the statements over here, right? So you will always waste work. One of them will be no ops. And the second is you're delaying this instruction. If you were doing branch prediction, this instruction will get its value because there's no ambiguity. Whereas here, there is ambiguity. You need to wait until this predicate value is resolved. Make sense? Now, some of you may think, why don't we predict the predicate? Right? People have actually proposed that also, but let's not go into that right now. You could predict the predicate too, but then it becomes more complicated. Okay, conditional moves, I've already talked about this earlier. Let me breeze through it. This is a very limited form of predicate execution that exists in pretty much all ISAs. Basically, you conditionally move R2 into R1 based on some condition, if the condition code is true. And this was the C statement that I discussed. And this is the operation. Basically, you can, again, it's a very similar piece of code written in a different way. You can implement this with 3 instructions without any branches. And I'll show you another example from ARM, but we've covered this in an earlier lecture. So what's the benefit of predicate execution? Let's take a look at it. This could actually be energy efficient also, especially if you have a deep pipeline, a hard to predict branch. Let me show you pictorially. Well, if you have predicate execution, what you do is, these are predicated. Well, control flow graph doesn't look like this if you have predicate execution, but assume that this is the normal branch control flow graph. You basically fetch from both paths, except the compiler has arranged the codes such that there are no 2 paths. That's what you do. And eventually, when the branches result, one of them turns into no op, and you're good to go with the rest, right? Whereas if this was a hard to predict branch, what would happen is you would flush the rest of the instructions. So it has saved you a lot of work that you have done. So this works really nicely if the branch is hard to predict. If the branch prediction accuracy is 50% for this branch, for example, maybe a good idea to convert that into a predicated execution mode. That way the branch is eliminated. But if the branch is predicted 100% accurately, it would have been predicted 100% accurately. This may be a bad idea because you're wasting work. Right? And you're also, there are some dependent instructions over here that you may not be able to execute because they're dependent on both B and C. Okay? So the takeaway is this could be very energy efficient and also high performance if the branch is hard to predict. Let's get back to advantages and disadvantages. The advantage is it eliminates branches. As a result, it eliminates mispredictions for hard to predict branches. And there's no need for branch prediction for some branches. Now, this leads to a lot of different advantages, actually. Remember, we talked about the branch prediction tables. if you eliminate the branch now, they're not occupying space here. And these were hard to predict anyway. Why are you wasting space on these hard to predict branches? You could argue that. So this has interesting interactions with branch prediction. It makes branch prediction more accurate. Eliminating those hard to predict branches from these tables, that makes branch prediction more accurate. And this is good if the misprediction cost, and this is a complicated equation actually. Compilers have a terrible time making this trade-off because it's tough. If the misprediction cost is greater than useless work due to predication, that's also hard to estimate for a compiler. Remember, compiler is doing this predication. It needs to make this trade-off. What's the accuracy of this branch if I let the hardware predict it? What is the misprediction penalty? These are both dependent on dynamic events. And the compiler is making this judgment that's profile. They're using the profiling, or maybe something else. Right? And what is the useless work due to predication? Again, that's dynamic, right? You know the size of blocks, but you don't know the frequency of execution of the blocks. So you don't know what the useless work is during the execution. So that's a tough equation. Itinium compiler had a very difficult time doing this, IA64. IA64 was a predicated machine, and I'll show you an example of that. But it's tough. There's also another thing. The compiler doesn't just take that into account. The other thing that it needs to take into account is how much optimization do I actually enable by combining everything to be straight line code, right? Because there's benefit coming from that too. So it's a very complicated equation to decide whether a branch should be eliminated or not eliminated. And I don't think anyone has figured out the best way of doing this yet. Well, this is the other advantage. This goes into that equation, but enables code optimizations hindered by the control dependency. Remember, I showed you a control flow graph maybe 2 lectures ago, and told you that eliminating branches can help performance optimizations because you can move instructions more freely within the single block of code. Well, that's predicate execution has that advantage. The disadvantage, it always causes useless work, right? But this is especially important for branches that are easy to predict. Because if you're almost 100% accurate for a branch, you're always executing some useless piece of code. And this reduces performance if this is true. Again, the compiler needs to judge this. If this prediction cost is less than the useless work. And this is a very difficult thing for the compiler to determine because completely eliminating a branch is not adaptive to runtime branch behavior. People have found, and we've done research in this, we've found, and others have found that branch behavior changes based on many things. Input sets, program pace, which control flow path you're following. So you really would like to adapt. And if you eliminate the branch, you've given up your choice. And of course, you need additional hardware and ISA support. That's kind of obvious. And we've discussed this also, right? You've told me that you cannot eliminate loop branches for good reason. You can reduce the loop branches. We'll talk about loop unrolling. And the idea is, over there is reduce the frequency of branches. Don't branch every iteration, branch every 4 iterations. That's the idea of unrolling. But you cannot eliminate all of them. So this is Intel IA64, Itinium. Each instruction can be separately predicated. That's very similar to actually ARM, if you will, except it has predicate registers. Each instruction carries a 6-bit predicate field. I think that's 4 bits in ARM, right? It's a condition field. Yeah, it's not a predicate register field. So it's a little bit different from ARM. And instruction is effectively a no-op if it's predicate false. And you can study this case, but this is basically predicating this control flow graph. Where this is code with branches, and this is code with predication. So one other advantage you see over here is code size is also reduced, right? I didn't put it up over here, but you usually reduce code size, unless you're doing some other optimizations with predicate execution, because you eliminate the branches. Let's take a look at ARM very quickly. I don't think I'll spend a lot of time because we don't have a whole lot of time. But basically, ARM instructions can include an optional condition code. And an instruction with a condition code is executed only if the condition flags in the CPSR. Is that the program status register?
Yeah, current program status.
Sure, that's right, yes. Meet the specified condition. So I've shown you this before. Basically, this is the condition field. And these could be different conditions. unconditional is always, right? It's always executed. Does not depend on any condition code, but these are all kinds of different conditions, some of which you will never get to use. But somebody will use, remember? Okay, well, I guess I'm not going to go into this, but basically this is add EQ. If the 0 flag is set, then execute this instruction. Add is unconditional. Condition codes, basically which instructions set condition codes, you need to specify it. Right? Add S, for example, sets the condition codes. Not all instructions set the condition codes. But let's take a look at benefits. I'll let you go through this because this is kind of trivial, but this is from ARM slides. This implements the greatest common denominator algorithm, and this is the flowchart of the algorithm. Basically, you test if R0 is equal to R1. If not, you do something, right? You subtract, and eventually you figure out which one's the greatest common denominator between two numbers that are stored in R0 and R1. We can think about this. This is simple. What does the code look like without predicate execution? Now, with predicate execution, this is what it looks like. And again, it's just an implementation of what's shown over here. You can study it. It's not that difficult. But again, what you see over here is with predicate execution, you get only 4 instructions. You still have branch for something else, basically, when you reach the end. But this is straight line code. Whereas with branches, it's much more ugly, right? You see a lot of branches over there. So you've actually saved instructions as well. Any questions? Okay. I'm going through this quickly because this is actually really trivial to look at. But I'll talk about some idealism. It's always good to try to be an idealist if you want to improve things. But wouldn't it be nice if this is true? If the branch is eliminated only when it would actually be mispredicted. Right? And if the branch were predicted only, when it would actually be correctly predicted. Basically, we'd like to do that. And also, wouldn't it be nice if predication did not require ISA support? It's a little bit tougher. But people have looked at this. People have tried to make this happen. And I'll give you the idea of the first one a little bit. Basically, what are the major limitations of predication? We've talked about a couple of these, 2 of these actually, adaptivity and ISA. It's not adaptive to branch behavior because branch may change. Branch may be predictable, not predictable. Right? It's applicable to loops and complex control flow graph too. So if you have a very complicated control flow graph, imagine predicating a very complicated control flow graph because you're really testing a bunch of conditions in a complex control flow graph, right? Where did I put this thing? Anybody can see my, oh. So this works nicely for small Hammock if then else branches, but what if your control flow graph looks like this? I guess I can go overboard with this, right? But you have a bunch of conditions that you're testing. And all of these are hard to predict. What do? Well, it turns out you end up executing all of these if you predicate everything, right? Because there are lots of conditions. But in the end, what you really need to execute is one path. Right? You predicated the entire control flow graph, but you're actually wasting, all of these will turn into no-ops depending on which branches are taken. Right? That's why compilers are conservative and they don't predicate huge control flow graphs because there's lots of wasted work. So how do we actually fix some of these ideas? Well, I guess I had this here. Right? If you predicate everything, then you actually have a lot of wasted work. I'll talk about the idea of wish branches. This is not implemented in existing processes yet, but I think this, going forward, it's a nice idea because it's a hardware software cooperative solution. I will not talk about dynamic predicate execution. This basically solves, hopefully, all of those problems, the second one partially. But let's take a look at the first one. Basically, we'd like to make predication more adaptive to branch prediction. adaptive to branch behavior. And the idea is, well, we'd like to execute the code as normal branch code and use branch prediction if the branch is easy to predict. Otherwise, use predication. The idea is to have the compiler generate code that can be executed both ways, either as predicated code or non-predicated code. And the hardware, based on dynamic branch behavior, decides which one is executed, either branch prediction or predicate execution. It's kind of nice because the compiler is good at generating code, hardware is good at dynamic decisions. It's a nice clean way of dividing work between the two. And if it's easy to predict at runtime, then use normal branch code. If it's hard to predict, then use predicated code. So how does this look? Basically, this is normal branch code, this is predicated code as we've shown, and this is the wish branch code, if you will. It's bigger than both, unfortunately. But now you have both predication as well as branches in it. And the hardware has a choice. So I'll go through this again. Let's say when the hardware comes to this jump instruction, this branch, which is equivalent to this one, what it does is it asks itself, is this easy to predict or hard to predict? And how do you do that?
By looking at the weak prediction or strong prediction.
So that's one way. Basically, this is called the confidence. How confident are you in this prediction? You could do that by looking at weak prediction or strong prediction, or you could have another predictor for this, right? In fact, processors implement different another predictor for this. This is called the confidence estimator. You can estimate the confidence of the prediction you're making. If it's high confidence, then you say, oh, I'm likely going to predict this branch correctly. And a confidence estimator may work on different information, right? Maybe you have a program counter-based table that says, that looks at the frequency of mispredictions for a branch, right? Okay. If that's the case, then the branch is predicted, and the predicate values are ignored. You set the predicate value as you'll always execute. Nice, right? And if it's predicted not taken, then you execute the fall-through path and you ignore the predicate values, and you execute the unconditional jump over join over there. It's really a jump. Make sense? So it looks like normal branch code execution, except you have some predicate values that you kind of ignore. If the hardware says, oh, actually, I'm not very confident about this branch, probably I'm going to mispredict it, then now you can execute the code as predicated code. It's beautiful, right? You have the option. What you do is you don't predict the branch. Now you ignore the branches. You still need to fetch them, unfortunately. You ignore the branches, but you execute the code as predicated code. So the execution looks like this, which is very similar to this, except you ignore the branches. And eventually, based on the outcome of the branch, something becomes null. Does that make sense? It's kind of beautiful, right? And this actually improves performance compared to both branch prediction and predicate execution. It tries to get the best of both worlds. Let me rush through this quickly. Advantages: it reduces the overhead of predication. Now, a branch hardware has a decision, right, to make. It can actually execute the code either as normal branch or predicated. Whereas if the code is set in stone as predicated, hardware has no choice. It has to execute it. Right? Now, the other upside is, because the compiler knows that the hardware can make the right decision, the compiler is a little bit more off the hook. Right? The compiler can be much more aggressive. It can say, oh, I'm going to predicate this huge chunk of code, and hopefully the hardware will make the right decision in the branches. Does that make sense? And the other thing is, remember, predication actually is dependent on the machine configuration, right? This is, if the branch, a branch that is easy to predict in one generation may become hard to predict in another, because depending on your branch prediction, and vice versa. And if the compiler predicated the code because it was branch is hard to predict in one generation, in a later implementation, that branch may be easy to predict because you have a much better branch predictor, right, 5 years later. But you're still running the same code. If you have these adaptive, if you have the ability to adapt between branching and predicate execution, then you can be much better. you're much more backward compatible. You don't, the predicated code's performance is less dependent on the machine configuration now. Of course, there are disadvantages, so it's good for you to think about these. Now you can have extra branch instructions compared to predicate execution, right? Predicate execution didn't have branch instructions. We can increase the code size again. And these could cause contention for branch predictor table entries. As we've discussed, predicate execution eliminated that. But perhaps the biggest disadvantage compared to predicate execution is we've eliminated one big benefit of predicate execution, which is now the code is not straight line code because we introduced these branches into the code. I don't know how to fix that problem. Maybe you guys will have a good idea after you finish this course. Okay. Yeah, we still have some time since you brought this up. So we'll finish this. This is a very simple idea. This is the last thing I'll cover in branch handling. And this is the idea of fetching from both possible paths. It's called multipath execution. Well, the idea is simple. Execute both paths after a conditional branch. Right? And this is a paper that actually analyzed it theoretically. What if you do it for every single branch in the program? Well, what they found out is soon the paths become exponential because you have a control flow graph that basically has lots of branches. And if you keep branching and executing different paths, eventually you'll be executing 2 to the n paths with n branches, and only one of them is correct. Right? So that's the disadvantage, I guess. But, you can refine this idea, and you can do the same thing we did for wish branches. You can say, only do this for hard to predict branches. That becomes more feasible. Right? You can use dynamic confidence estimation. If you're not confident about the prediction, then execute both paths. Advantage, it improves performance if misprediction cost is greater than useless work. Because now you're doing useless work also, right? Because you're executing a path that shouldn't be executed. The big advantage is no ISA change is needed. You just need to figure out 2 paths and go down. The hardware needs to be changed because you need to be able to have 2 sets of register files, right? Because these are different paths. Really, you need to have a context for each path. Now let's take a look at that. Each file of path actually requires its own context. You need to have a program counter, you need to have registers, and you'd better have different branch prediction structures, at least a global history register that's different for these different paths, because you want to predict the branches correctly in different paths. And by definition, you have different histories for different paths, right? So you've got to be careful when you actually implement this. And we've already talked about this. What happens when the machine encounters another hard-to-predict branch? We execute both paths again, and that may be a good idea. So paths follow quickly become exponential. You're wasting a lot of work waiting. And wasted work, we already talked about that. Right? Well, wasted work exists, but it's especially annoying, if you will, if paths merge. If you have, well, it's gone right now, but if you have a Hammock branch, and if you do this for the Hammock branch, which I'll show in the next slide, well, paths merge, and if you didn't detect that, you'll be executing both paths and the same code, right? Except the data values may be different. Okay, so let's take a look at the difference between dual path execution versus predication, and after this will be done. If this is hard to predict, what dual path execution does is creates 2 paths after that branch. And the machine follows those 2 paths. You have 2 contexts, and these paths should not interfere with each other. They should not update each other's values, right? And this is what happens. Both paths, you execute the same instructions, right? Well, you have to because the data values may be different. Whereas with predication, predicate execution, you can think of it this way. You actually execute both paths, but then you have only one path right here, right? You could think of it this way, right? Because the code is really straight line codes, B, C, D, E, F, right? After the control flow merge point, you don't do useless work. Whereas here, you're doing useless work even if the control flow merges at any point. Make sense? So this is one big disadvantage of dual path execution over predication. Okay, I think I'll stop here. In the next lecture, we'll start with how to handle different branch types. Yes?
I think you should be able to get around that though,
Uh-huh.
because you're not actually committing values back or writing back to the register file
Uh-huh.
until after you know for sure which side of the branch would have been taken.
That's right.
Because of like the pipeline flow. So like you should be able to do like the predicated path and then just not write back the value from C or B.
But do you fetch from different paths? If you fetch, now you're wasting slots in your pipeline.
So I guess if you're fetching
Both paths.
both paths into your pipeline separately, then.
Yes, that's the problem. Now you could argue that you could actually not fetch from both paths, recognize it somehow, and do something similar to this. Then it becomes not dual path execution, but really predicate execution done in hardware. But you could do that also. People have proposed that. Okay, so remember next lecture, Friday, is a review session. So come up with questions. Okay.
Have fun
See
on
you.
your trip.
Thanks.